into, but I don't.
I'll go that way.
Yeah, I put a slide up so you can see the physicist talk. I'll talk about it a little bit, but we'll put it into real language for you.
I'm getting too old to learn a whole lot.
Oh, I hear you. All right. So we get going. Greetings. I'm Cary Altman KB0HV. I've been studying the sun since I was 15 years old. So that's about 45 years ago. Used to make charts and drawings and all that stuff. Really tried to use the sun to predict my band openings for my brand new ham license. And got a lot of fun out of that. So this is how the sun looks during an active portion of the solar cycle. We are not there. None of those orange dots or yellow dots are there on the sun right now. We have a spotless sun. We've been spotless for about 27 days now. So we're definitely nearing the low end of the cycle. So speaking of cycles, there's the last 3 cycles. That's where we're at right now. And you can see the bottom part of the chart there isn't quite filled in, but we're starting down that 5-year slope down towards the minimum. Somewhere near 2020 is where we're gonna hit the bottom. And also note the downward trend in the power of those cycles as we're nearing this minimum here. We're at the end of what's known as the modern maximum. And I'll show you another chart that shows all the recent solar cycles here real soon, but you'll see why we're in the maximum right now. Also note the increasing time between the cycles. At the bottom, there at the left side of the chart, I forgot I had this fancy laser pointer. Over here and here, you can see that we bottom out and then start back up again real rapidly, like within a month. This last solar cycle, if you remember going into cycle 24, 11 years ago, we stayed at the bottom for about 3 years. We were begging for sunspots, like when's it going to end? And it finally started up into cycle 24, but with that really extended downtime at the minimum. Well, they're expecting this downtime to be really dramatic. If the charts hold true, we're going to have a very extended minimum. So we'll get more into that here. So, hi, Jack. Our sun is a middle-aged star. It's very old. It's about 4.5 billion years old. And it will keep increasing in temperature, brightness, and size in the years ahead. The sun's radius has grown by 6% in its lifetime. And it now has enough hydrogen fuel to last for about another 5 billion years. And that puts it just short of middle age. When the sun's about 7 billion years old, it'll start slowly beginning to change. It'll become bigger and it'll become cooler. By the time it's 10 billion years old, it'll have changed into a red giant, and its atmosphere will stretch out to near where the Earth is right now. Of course, we won't be here.
Speak for yourself.
So, these are the known cycles that we've actually charted these cycles clear back in the 1750s. Now we studied sunspots earlier than that. A lot of the early scientists, they were counting sunspots. They had a way to count sunspots. So we actually have a sunspot record that goes back into the 1400s. But, so we can gain a lot of information from that. We don't have fancy charts here and everything. But notice what's happened here. What's that there? These cycles were fairly small and kind of, it was kind of random. But then here, the recent centuries, about the last century and a half, we went into a maximum period where the solar flux really got up there in the 200s. Notice on the other charts, we don't have 200 anywhere. But right here, 1960, 1972, if you were around as a ham radio operator there, it was amazing conditions. And so we've been kind of peaking way up high here towards the end of this. I'm going to show you that this is actually a cycle that started way back, well, back about here, about a 400-year cycle. And we're reaching the end of that 400-year cycle right now. And so we reached, this is called the modern maximum right in here. But we're starting a downward trend here. And so we'll get into that just a little bit more.
The numbers on the left there on the graph, they are,
That's solar flux.
That's how many solar spots it was.
Well, that's not the sunspot number, that's the solar flux number.
Okay.
So,
and the better,
the higher it is, the more ionization we get. And so the better radio conditions are.
the higher it is, the better.
But it's also the higher that is, the more the Earth reacts to the sun. You know, every time there's a sunspot, there's a wave of energy that hits the Earth, and it jostles us. And so those peaks, that amount of energy that hits us at any one time has gone way, way up here in the maximum period. So in this short time we've been here on the Earth to observe the sun, we've only kept records of the sun's activity for about the last 400 years. We basically have a snapshot of what the sun's doing now. And lately, with modern statistical analysis and computers, we've begun to understand that there's many repeating patterns in the sun's sunspot activity. The most pronounced pattern is the one we all know about, the 11-year cycle that we've got here. But what have we learned in this short 400 years? We still don't know very much about how the sun works or why it does the things it does. There's still 4 fundamental things that we don't know about the sun. And this is physicists speak here. But the first thing that we don't understand about the sun is the surface of the sun is about 10,000 degrees Fahrenheit. The atmosphere of the sun, the corona, way hotter. It's 1,800,000 degrees Fahrenheit. Way, way hotter than the surface of the sun. We don't understand that. How can that be? Solar flares. We don't understand solar flares. They just heat up. They blast tons of material into space, but we don't know why. We can't predict them. We don't know what causes them. The whole 11-year cycle, we don't know why it starts, why it stops. The sunspot number goes from 0 up to around 200 or so, and then it goes back down to 0 again, and we don't know why. And then there's the missing neutrino theory. If the sun's a nuclear furnace, it should be giving off a certain amount of neutrinos. We can predict that. We're getting maybe a third of what we expect here on the Earth. We don't know why. So we're still kind of babies and infants in understanding the sun. So we're going to look at some long-term predictions. Here's a rough graph of 400 years. And early records show that sunspots, the sun went through a period of inactivity in the late 17th century. They're the Maunder Minimum, they're in red. Very few sunspots were seen on the sun from 1645 to 1715. And although observations weren't as extensive as they are now, the sun was in fact very well observed during this time period, and the lack of sunspots is very well documented. This period of solar inactivity also corresponds to a climactic period called the Little Ice Age. And this is when rivers that were normally ice-free froze, and snowfields stayed year-round. It's during this time, there in the Maunder Minimum, the River Thames froze so solid that people would ice skate along its length for 7 years in a row during that. 2 years during that time period, it was recorded there wasn't a summer. It just stayed cold. So we had another smaller dip called the Dalton Minimum right here in the early 1800s. And it cooled down a little bit then too, but not nearly as dramatically. And you can see, we were talking about the modern maximum. This is the first chart. The numbers were smooth, so you can see quite how high the tops got. But you can see here in the modern maximum, we've really peaked out. And the only other time we even saw anything close was right in here. But so we've really with all that sun activity there, the Earth is warmed up, along with greenhouse gases and all the things that you hear about with global warming, folks. The sun was also more active. And so, of course, we warmed up. We are in a period of global warming. Now, whether it was man-made or not, that's the debate. I tell you, it's the sun. We're so tied to what the sun's doing. So, we've observed 24 cycles of solar activity. Using modern mathematical techniques and statistical analysis, we've analyzed all the numbers, and we've noticed a lot of trends in how long and how intense the cycles will be. We're just now getting to the point where we can attempt to do some long-term predictions as to what the sun will be doing. And using data from previous cycles, we can see correlations in the current cycle, and it helps us make more accurate predictions right now. So, here's an interesting chart. This is all the minimums that we know of, clear back as far as we can see with carbon dating and everything else. All of science has come together to produce this chart. And we can see that there's regular intervals of minimums. The rings in trees show it to us, the rocks show it to us, carbon dating shows it to us. We know that these minimums existed. So, again, another chart where you can see the minimums. We've had a couple of little mini ice ages where it really got cold for a number of years. Definitely the Dalton minimum, the Maunder minimum is like back in here. And then, of course, our modern maximum, our modern warming period. And look at this projection for cycle 25.
So they're predicting another ice age or what?
I think so. So, look at this chart here. This chart shows how similar different solar cycles are, the 11-year cycles, and how they track with each other. The black line that's not all the way across is showing you the average of all these. But we've got a good idea of what an 11-year cycle looks like, just in the 24 that we've observed. And we know that they pretty much always now, at least here in the back end of this 400-year cycle, we're noticing that they have a double peak. Every one of our cycles has a double peak. Didn't happen that way in the early part of the 400-year cycle. Still something we don't know. We don't understand why. But what we're able to see from this, here's all the 24 cycles. Well, there's 22 of them there together. And you can see how closely they correlate. So we know we're on to something there as far as predicting the intensity of an 11-year cycle. But now, we've got some other interesting cycles that we found using the computers and using statistical analysis. We've actually identified now that there's a 22-year cycle, a 52-year cycle, an 88-year cycle, 105-year cycle, a 212-year cycle, and the 420-year cycle. And so this kind of blew our minds, but when we look back on the charts, it helps us predict, and we can see that there's some validity to this. So, more into the physics. How are we doing this? How are we predicting these things? There's basically three major methods that the top solar physicists are using to predict the next solar cycle. And some of them are more accurate than others. I'm just putting them out here for reference. We're not going to really go into them. This next chart kind of explains them all in physics speak. But these are all pretty much new theories. It's come into like the last 100 years or so that we suspected those cycles were there, but we just didn't know how to do the math. And they're just now figuring that out. So there's basically about 5 major theories how to predict future cycles. And so there's 4 of them that really stand out and are more accurate than others. So those are the 4. And we'll show you charts on these. But you've got to realize that all these ways of seeing patterns in the sun and all this stuff, I mean, as far as the lifetime of the sun goes and the length of time that we've been studying it, it's just that in the lifetime of the sun. We really haven't had a lot of time to figure all this out yet. And so all these 4 predictions that we apply to this next solar cycle coming up, the predictions aren't good for the near or the far term. The cyclic downturn in activity that we're about to go into happens about every 100 years or so. And then, and of course, the cycle 24 and 25 that's coming up fit right into that cycle. But we're also lining up with the 400-year cycle and the 212-year cycle. And it just speaks of doom as far as solar activity here. So the question we got to ask, outside of ham radio even, I mean, we know that the sun affects our propagation, but how does this correspond to the Earth? I mean, why does it matter to us on the Earth what the sun's doing? And so this again this is one of the theories showing how he predicted the Dalton Minimum with his math and the Warrensburg minimum and the modern maximum. So the math is working. So here on Earth, when we have a weak maximum, there's fewer solar events, there's less particles hitting the Earth, there's less superstorms on the Earth because there's less activity feeding it, and there's less satellite drag. And satellites decay in orbit because of particles hitting them and slowing them down. And so when we get a strong maximum, you get a whole lot more of that. It's hard to keep satellites up in the air. Satellites being destroyed by particles just going right through them. It's just really, really hard. GPS satellites are affected. When we get really, really strong outbursts from the sun, it actually rocks our geomagnetic field. It buffets it. And so the whole Earth's geomagnetic field, when you hear the geomagnetic field is active, that means it's moving. When you hear it's unsettled, it's really moving. When we're having a storm, well, it's just totally wild up there. And what's happening is these solar particles, the solar wind is hitting us so hard that the Earth's atmosphere, the geomagnetic field, is just shaking and rocking. And what does that do to us? Imagine all the power lines out there, hundreds and hundreds of miles of wire out there, and you've got a magnetic field rocking back and forth. What's it going to do? It's going to induce currents in those electrical lines, drives them nuts. Or you can blow out power grids that way. So that really affects us. Ham radio operators definitely see it. But the thing that they don't want to tell us right now, because they've been trying to scare us about global warming and all that stuff, this also has a big correlation with the weather. We can see the blue line there is the temperature. We can see that in periods of high solar activity, the temperature on the Earth goes up. When the sun cools down, the temperature goes down. It's logical, it makes sense, but they want to tell us that that doesn't happen, or that man has more influence on the Earth's temperature than the sun does.
Yeah, ask a volcano.
They say carbon dioxide is a big pollutant that man creates and affects the weather. Here's the fact. One eruption of a volcano puts out more carbon dioxide than human beings will produce this century. We have very little to do with the weather, unfortunately, according to the global warming people. But you can see on this chart, I mean, there's such a strong correlation to the solar activity and the temperatures.
Fortunately, if we're headed into a new ice age, we need all that global warming.
You do, and it is, you know, let me go into that because I don't want to discount the effect of man. We have put out greenhouse gases, we have messed up the ozone layer, and we have created this insulating blanket around us that's part of our atmosphere, and it is retaining some of that heat. And since we're in the active period of this 400-year cycle and the sun's activity is way up, of course we're warming up. When the sun turns off, it's a whole new ballgame. I don't care how many blankets you got over you, without the sun heating us up a little bit, we're going to cool down.
If we had another minimum like Dalton, would we be able to warm the earth up?
A small one like that, I mean, it's just, it's going to take years to really affect the average temperature. A whole lot, to go into an ice age. But several years of inactivity can spur a lot of interesting things, like the severe weather that we're having right now. We're seeing a whole lot more severe, you know, it seems like big changes, big severe storms that shouldn't have been severe or wouldn't have been during a normal period. But because the sun's output has been so strong and now it's not, that sudden change is what's affecting things so much. Jack, did you have a question?
Yeah, for one thing, the problem's not that man is creating global warming. It's that he's accelerating it by about 10,000 years.
Exactly.
And there's talk, all kinds of talk about wanting to terraform Mars.
Yeah.
Well, Mars at its closest point to the Earth is 34 million miles. It's over 100 million miles at its furthest. It's a lot cooler there.
A lot less atmosphere to
A lot
hold it
less
to.
atmosphere, less gravity.
They say the first inch of Mars is pretty climatic. You probably live there.
But they're talking about terraforming it,
Yeah.
which with modern technology is a 10,000-year project in itself.
Well, there's a
The point is that if they can create a global warming on Mars, and there's several different theories on how to do that, as far away from the sun as it is, it would actually heat the atmosphere up way past what the Earth is, and it's a much thinner atmosphere.
Yeah,
It would create a greater atmosphere, would bring moisture out, it would melt the polar caps, bring water out, and bring water out from the ground. The point I'm trying to make is the sun has a great effect on the Earth. Oh, and by the way, solar flares, from what I understand, are caused through the magnetosphere. When when magnetism creates a knot, you have a solar sunspot.
I've got a slide that talks about the magnetism.
And when it snaps. But anyway, the sun has a different effect on the planets than the atmosphere. You can create global warming with very little sun.
Right. Well, there's a third thing going on here on the Earth too that we don't talk about a lot, and it's negating the global warming. And a lot of farmers will know about this. Farmers have an evaporation tank that they measure. They're looking at the intensity of the sun, the ability of the sun to evaporate the water in their tank. If you took a measurement from the 1960s and compared it to what's happening today, the sun doesn't appear to be as powerful. It doesn't seem to be as bright or as hot. It's not that the sun has cooled down. We've got so many particulates in the air that we've blanketed the Earth. And a lot of the sun doesn't hit us. It's hitting that instead and warming up the atmosphere instead of the Earth. We saw a dramatic example of that on 9/11. They grounded all the planes in the U.S. And without all that plane activity and all the particulates that they put in the atmosphere for that 3 days, the temperature went up. Went up like 3 degrees in 3 days. That's incredible. That was incredible. We saw amazing correlation to the particulates and what we were doing.
Particulates fell out of the atmosphere.
Yeah. They say that's why so many people have asthma these days. It's all this rubber and all that stuff in the air. So anyway, let's move on. So we do see a correlation with the weather and the sun. Very strong correlation. And this is another one. Shows some more effects. It shows the effect of volcanoes, what volcanic ash can do. But the main thing here is along solar activity. You can definitely see that correlation. All right, so now get into some statistical analysis. The reason we're worried about this next changeover, the cycle 25, is because of the very strong correlation between our last 3 cycles. That's 22, 23, 24, and we're coming into 25. These last 3 cycles are almost identical to cycles 3, 4, and 5 in the late 1700s. Almost identical. That's a little scary. So, it looks like if the last 3 cycles correspond to 2, 3, and 4, and cycle 25 is going to be the same as 6, it looks like the Dalton minimum. If you line up these charts along with the modern charts, you line them up with what was happening there at the Dalton minimum in the 1800s, it's identical. But we don't have enough data points. We think we're at the end of the 400-year cycle, which means this next downturn isn't a Dalton minimum, it's a Maunder minimum. And it corresponds to the 400-year chart, so the minimum in the 1600s. And that one lasted about 80 years. And so if we get an 80-year downturn in the sun, I guarantee you it's going to cool down. And none of us alive today are ever going to see another solar cycle like the 72, where you can talk to Europe on a coat hanger with 1 watt. It ain't going to happen. That's one of the reasons we're developing all these satellite technologies, digital technologies, and all that stuff, because we're not going to be able to propagate using HF as easily as we used to. If there's no solar activity, it just isn't going to happen. So we have no idea how long this minimum is going to be. Some of the predictions methods say it's going to be 50 to 80 years or longer. Some don't know. If it's a Dalton minimum, it's about 6, 8 years. So this is bad news for everybody, not just ham radio operators.
Cary, I just wanted to clarify because I was looking online for different charts and weather, and just to clarify this, so the circled area here, that's not the time of the ice age that happened in England, right?
This is the mini ice age that I've circled here.
But that was the one that happened in England?
It happened all over the world.
All over the world, but that's when the things froze. And
think about where human culture was.
Right, Europe.
I mean, we were just starting the economic age. People were just starting to come out of tribal and starting to do commerce around Southern Europe and stuff in the 1700s. And so we were just starting to migrate. And so along with that came written records and all that stuff. But
Cary, I think you're talking about the 1600s, so she's talking about what you got circled there in the
Yeah.
1800s.
Yeah.
well, oh yeah, you're right.
Yeah, that's what I was kind
You're
of.
right.
Sorry, I was a little. I thought it happened earlier, so.
How did the Dalton minimum compare to the Maunder minimum?
The Maunder minimum was a lot longer, a lot deeper. And this is the Dalton minimum here.
Okay,
that helps a little bit.
Yeah, the
See right there in the 1800s, just past 1800, that's the Dalton minimum.
Oh, okay,
Right, right in there.
Yeah.
The Maunder minimum, now look at that.
Yeah, that was the mini ice age.
Yeah.
The Maunder minimum. So that period of time, is that where we're headed right now?
That's where we think we're headed.
And
So we
so-
just don't have enough data points to know whether or not we're here or here.
So what are they saying looks more identical? Because you were saying it looks identical to.
Comparing the last cycles right in here to what's happening right now, they look almost identical. But the problem is, is we don't know what it looked like here, really.
Okay.
We don't have charts.
All right.
And so I'm betting that the last 3 cycles that we've been in are very identical to these 3 cycles, too. We just don't know. We was making charts back then. They were just counting sunspots.
How did they identify the 400-year cycle?
We see it, one of those theories I showed you, the 4 theories of how we analyze the sun. One of those, you can clearly see that regression, that repetition,
Or what did they base that on?
just the past cycles. The peaks and when they occurred, how far they occurred from the maximum and the minimum. I mean, it's a lot of fancy math in there.
Basically, cycles within cycles. In other words, you can see this cycle's going up, and then it goes up, goes up, goes up, goes down, goes down, goes down. And the way the arch is looking, they think it's around 400 years.
But
Based on this data, I don't see 400 years of data.
No, so what I'm saying, you won't.
400 years start back here.
Yeah.
Also,
So
Yeah.
about 1630 or so is when we think the mountain minimum started. And so count it 420 years from there, and we're about there.
We do have some data points earlier than that. This is pretty much our science recorded data points.
Right.
Earlier data points we have from that are things like growth rings and
Carbon dating.
stuff we're pulling out of the ice and things like that.
Right, exactly.
quite literally what Chinese was doing with floats.
Well, like that one chart where I showed you all the minimums, clear down to
Yeah.
year 0, and that's where we're getting all that, is from the carbon dating, the rings, and the rock strata, and all that stuff. All right, so we were talking about magnetism. Why are scientists so sure that this is happening? Well, there's flows in the sun, magnetic flows, and we think what happens in the 11-year cycle is that there's a buildup of magnetic fields at each of the poles, and then whatever the mechanism is, it just flips. North becomes south, south becomes north, and that's when the new cycle starts. And it just changes polarity. And we've noticed that the strength of those polar fields when the new cycle starts really corresponds to the strength of the cycle that's coming up. And so we noticed that there were very weak polar fields in 2008 going into this current cycle. And of course this one was kind of a dud. Whereas in 1986 we had a really strong polar fields. We could measure it, we could see it. And it flipped real dramatically, and we had a really strong cycle 22. So all this math is coming together, but we're just so new at this. We don't know what we're looking at. So this time, instead of building up for a polar flip, the polar fields just been slowly reversing at the maximum, and they don't look like they're getting any stronger. And then they didn't really flip; they just kind of lazily moved. And so we think that this next solar cycle is just going to be really weak. Everything points to it, but we just don't know. We're just so new at this. This is our first time seeing a 400-year cycle, and so we just really don't know if we're going into a Maunder minimum or a Dalton minimum, and we're going to all experience it together. And the human race is going to learn a lot about the sun here in the next 20 years. So we do appear to be going into an extended minimum, though, and following any of the major prediction models. We stayed at the bottom for almost 3 years going into cycle 24, and the upcoming minimum 5, or about 3 years from now, 2 years, promises to be even further extended. No one knows yet. It's going to be a relatively short, quiet period like the Dalton minimum in the 1700s, and last 7 to 9 years, or a more extended one lasting 50 years or longer like the Maunder minimum in the 1600s. So, in either case, the next 15 to 20 years promises to provide less than optimum band conditions. And, of course, we also are going to experience colder than normal global conditions, if not another mini ice age. So, let's get to short-term predictions. I mean, this is what we use for radio. The sun has another cycle that we experience every month. The sun is actually revolving, and it goes around once every 27 days. And so a sunspot that's pointing at us right now, it revolves around, and then 27 days later it comes back.
I thought the sun rotation was 11 days.
No, 27 days. And so what we don't know is whether that sunspot that comes back around, whether it's going to still be there, whether it's going to be more active, less active. We had one, it kind of surprised us here last month. We had a couple of good spots hit the sun and got the solar flux up to 72 or so and had some pretty decent conditions. And then it comes back around and it was just, they call it a plague. That's the scientific term for a sunspot that just, poof, it just wiped itself out. It's just a remnant of itself. And then it was gone. We don't know why, but you know, it's the bottom of the cycle, so that's what we expect. So, short term, we know that the sun does this 27-day thing, and we can predict that. We can chart what the sun does now, and then know that 27 days later, we're going to have similar conditions popping up again. And so, back in the day, the only way to get this data was to monitor WWV 18 minutes after the hour. They do that propagation bulletin that gives you the solar flux A index, K index, and what the solar field is doing. And when I was a kid, at least once a day, I'd set an alarm or do whatever I had to do to get that bulletin off WWV, put it on my chart. And those were the only charts that existed back then. You could send off to the Bureau of Standards for a printout that was always months behind. And you know, now you got the internet, and all this data's out there. Things are so much easier than when I was a kid. There's tools out there available for us to predict propagation paths, the maximum usable frequency, band openings. You do a Google search, and you'll get a list of at least 10 really good propagation prediction programs. And most of them are collecting the data that comes out of the WWV and the Bureau of Standards. This is a typical chart of the data, and they'll just give you the solar flux, the A index and K index, and this is what you chart, and then 27 days later it comes back. But a lot of these programs you get out there, they just automatically go into this database, and then they do their magic on this, and they'll provide you the charts and all that stuff. So you don't have to do the hard work anymore. You can just download the data. But if you want to do it the hard way, you can. What's this? Oh yeah. I basically talked about that one already. That's a bad slide. I don't like this slide or that one. But you can see right here, the dotted line is the predicted value. And you can see that the actual value didn't quite reach what the predicted value was, but you still had to peak right where it was, and you just kind of know where the sun is at in the 11-year cycle to figure out whether it's going to be stronger this next 27 days or weaker. But you can pretty much guess the day. So a lot of you have seen my predictions, like my field day prediction on Facebook and all that stuff. This is how I do it. I just get the 27-day data, and I can look at this chart, and I can see where the peak's going to be. But then knowing what I know about the sun and the geomagnetic field, imagine you got a quiet Earth, quiet sun. And everything's cool, everything's all just quiet and happy. And then all of a sudden a sunspot happens. Boom! You get the solar wind hitting the Earth. Everything rocks. So the first couple of days of solar activity, you'll notice usually that along with that rise, you're going to see a rise in geomagnetic activity. The Earth's geomagnetic field will get active. It'll get unsettled. And conversely, on a downward slope, as the sun stops hitting us with all that stuff, then the Earth quiets down. and the geomagnetic field isn't as active. So usually, the best time to get on isn't right at the peak, when the Earth is still reacting to this. It's right in this slope right here, as you're starting the downward slope. That's the best time to get on.
Can you define some terms for us? What is the solar flux and indexes, and how do they affect the propagation?
The solar flux, they're doing a sounding of the atmosphere at a certain frequency. They're bouncing it off and seeing how much comes back. And that calculation gives them the solar flux. And so they do that several times a day, and they get an idea of just how reflective the geomagnetic field is, and how much energy it caused that to happen. And that's our solar flux number. The A index is a reading that they take several times a day just to see how much motion is in the geomagnetic field and how active it is. And that number can go anywhere from 0 to 400, I think. It can get really, really active. We don't usually see that, but anytime the geomagnetic field is above 7 or 8, then you've got some kind of activity there. You've got some kind of storming. You've got a possibility of aurora and that kind of thing. The K index is a planetary average of what's going on, both dark side and light side of the Earth, how much it's reacting, and so it's an average. And so, of course, a planetary average, you want it to be as low as possible, the quiet conditions. And there's a lot more science behind it than that, but that's kind of a general explanation of what those
So
three
if the
are.
geomagnetic field is active, you're going to have a lot more background noise and
Yes, you'll have a lot more background noise and stuff on HF, a lot of QSV, fading in and out. Whereas on UHF and VHF, it's the opposite. You get tropospheric ducting, you get aurora, you get all kinds of cool stuff that happens during an active geomagnetic field. So on VHF and UHF, you kind of want to see a lot of activity in the geomagnetic field. For DXers and stuff like that, it drives repeater owners crazy. But then on HF, you want it just to be as quiet as possible. The highest solar flux you can get without a lot of A index and K index. That would be your best conditions.
for HF.
Yeah. All right, so let's see where I'm at. All right, so here's one. And this isn't now, we're not having solar flux anywhere near this. Right now, our solar flux is just hanging right around 80 or so, and it's just kind of flatlined right in here. But this was about 3 years ago, and we had actually some solar activity. And you can see, right as this solar flare hit, and the solar flux started going up, look what the A index did. It went up too. So it reacted to it. And then after we hit the peak here, it just kind of leveled out a little bit. We got another solar flare right here. Boom, got more activity. You can kind of see how these correspond. They don't exactly line up all the time, but they're usually close. And then, so you just kind of gauge these two to find out when your best time to get on. A lot of the computer prediction programs will go further in the analysis than that, and they'll actually give you maximum usable frequency and what bands are going to be open and what aren't, and that kind of stuff. So those are really, really handy prediction charts using the 27-day data. And of course, these are just, snapshots of the sun. Just, what's going to happen next time it rotates around. It really isn't long-term at all. All right, so here's some of the programs you can get. There's just a whole bunch of them. They're all pretty good, and they all take a little bit of studying to figure out what they're trying to show you and stuff. They all have some kind of scientist or amateur scientist running them and showing you all kinds of cool stuff. They're all worth checking out, but they're just all automatic anymore. It's just so nice these days to be able to jump on one of these and it goes out and grabs the data for you. Some of the logging programs even do it for you nowadays. So It's a good time to be around. So, let's see. Oh, okay, I wrote some of this for this last one. I got distracted trying to answer your question, but I knew it was here somewhere. So, what do these charts tell us? A sudden appearance of a large sunspot or a group can jolt the Earth's geomagnetic field. When this happens, this field becomes unsettled, the absorption rate goes up. And noise on the bands increases, it becomes difficult to skip a signal off the ionosphere. And if the sunspot's a strong one, we can experience geomagnetic storms. And these can cause radio blackouts on HF. They can also conversely set up sporadic E-skip and make conditions ripe for tropospheric ducting and auroral skip on VHF frequencies. So, when we look at the solar flux number, the higher the number, the more ionization occurs. The higher the MUF, the stronger skip and band openings that persist all over the globe during the 24-hour day. And then the A index, the geomagnetic field will get upset when a new spot shows up on the visible disk. The larger the spot or flare, the greater the reaction on the Earth. After the field quiets down, the rest of the time the region transits off the visible disk and the geomagnetic field will remain fairly quiet. And so this is why the leading edge of the rising solar flux might not be the best time to get on the air. Best times are after the peak is found, it levels out, and just starts back down. So, some of the best resources out there, of course, ARRL does a weekly propagation thing. NOAA has their thing. There's several private ones out there. That last one there, WM7D, I like the guy. He's kind of like me. He's an amateur scientist, but he just religiously puts his data out there all the time. And a huge amount of information there for everybody. So I highly recommend that.
Do you ever watch Tamitha Stove's reports?
Yes. Matter of fact, Tamitha just accepted my friend request.
All right.
So, yeah, I let her know that we put a lot of her stuff on our Working Ham page, and that she should like that page. She hasn't done it yet, but I think she will.
What was it called?
She's one of my heroes.
Tamitha Stove is she's known as the solar lady.
Solar.
She reports all the solar conditions for NASA. And she's on Ham Nation's podcast.
Oh, yeah, I've seen her.
Just on,
And-
is she on,
And she just got her ham
is
license
she
too.
on
so-
YouTube?
She is on YouTube,
Yeah, it's Tamitha.
Tamitha Scope?
Stove.
S-K-O-V.
S-K-O-V.
She's Twitter and a bunch of stuff too. All the
I
time.
know you put it on Facebook about you'll share them, and I'll watch them.
Yeah, she does I think a weekly YouTube thing. And I try to put those up on the page. Because they're always really interesting. And she's talking about just all this stuff. I mean, we were having some pretty strong flares there 6 months ago or so. Did you realize that a flare is dangerous to you? I mean, you see a lot of the stuff that happens on the news media, and they try to scare you. Oh no, the solar flare. If you're down here in the Midwest, it really doesn't bother you that much. But if you're flying in a plane, you're up in the atmosphere, going across the North Pole, and there's a big solar flare, your cancer risk just went up. There's a lot of radiation there. Occupants of the space station, you know
Well,
what?
that's what I was just going
You
to
know what they do during a solar storm?
protect themselves.
They are clustered behind the main instrument panel because that's where all the bulk of the stuff that will block it is. And they huddle there together with their eyes closed so their vision doesn't get affected. That's the only protection they have.
I just want to put this in some kind of perspective for myself, like, because I'm kind of a visual. So, again, reading online while you were talking at the same time, that a sunspot is basically a storm and it's actually cooler, and that's why it's black. So, a flare, is that different than a sunspot?
For some reason, the mechanism of the sun, when it ejects the material that you see, like a dramatic solar flare, you'll see a picture of it, a big arcing
Yeah.
thing that comes off the sun. That's hotter than the surface of the sun.
But the sunspot isn't? Or,
Sunspot is actually a cool spot.
okay, it's a cool,
And
okay.
It's a
all right.
cool spot, it's a cool spot, but for some reason, during higher solar activities, when there's a lot of sunspots, and they don't know why, they've measured the outside temperature of the solar system during those times. But for some reason, planets with atmospheres is affected by them. The Earth go up, Mars temperature with a small atmosphere goes up. They even see some activity that's stronger in Venus around heavy. They don't know why. The temperature in the solar system don't go up for no reason.
We just really don't
See, that's what I was,
understand.
yeah, that's what I was wondering, why it is that when the sun, you know, when all these flares and everything, and so that's what I was kind of thinking of Earth, when we have our storms and stuff,
Well, it just
you know,
goes to-
that doesn't, does that go outside of the atmosphere, does that go outside the ionosphere and all that? I know
No.
the sun is very powerful, I understand, but, you
Well,
know.
the sun, I mean, there's so many things we don't understand. It doesn't take a solar flare to hit the Earth with stuff. There's things called coronal holes on the sun, which is basically a dark spot. It's a hole as far as we can see. We don't really understand what it is. It seems like a cooler region, but that thing just sends out a solar wind at us that is just incredible. It doesn't take a solar flare to affect the Earth. These coronal holes, as they rotate into the Earth's target area, that'll buffet us bigger than a solar flare a lot of times. And the last couple months, that's kind of what we were dealing with, was these coronal holes. And so you got several things that happen in the sun. We got proton emissions that come out of some of these things. We got X-ray, M-class, C-class, all these different classes of solar flares that put out different things. Some of them put out just X-rays. Some of them send out protons, and we just don't understand the difference. But yes, those are cooler areas. They seem to be magnetic areas of some kind, but we just don't understand the mechanism yet. We're just, you got to realize that we as human beings, well, first of all, in the life of the sun, we're nothing, but imagine this. We've only been playing with electricity for 100 years. We know nothing. We're babies. So we're just starting to figure this stuff out. But
And I guess I was thinking about the, Star Wars, guys, when Princess Leia kind of, if you haven't seen that flying Superman thing and how ridiculous that is, the bombs that dropped that should have actually just floated everywhere. So that movie's ridiculous and should totally be redone. But anyway, besides the point. But I was just thinking how in space, how really the sun has that air pushing out, pushing, the wind. There's really, atmosphere kind of has nothing. So I guess I could just picture how strong that wind would be if there is no, if there's nothing. You guys know what I mean?
It's not air.
Well, first of all, it's not air. It's
Yeah,
water.
Well, right.
It's
It's a
charged
vacuum.
particles.
It's a vacuum. So sorry, not air. But it's a vacuum. So if you have a wind in there, I can picture how strong that could be because it's a vacuum. So
It's a wind of particles.
yeah, it's kind of. So I guess I could see how it could affect Venus and Mars and the Earth, and it's really very fascinating. I'm sorry I'm asking so many questions, but it's
Well,
just very fascinating to me.
that energy pulse that comes out of the sun constantly is actually, Einstein named it, he called it the Unifying Field. It's the field that creates our solar system. All the planets in 48 million miles apart from each other in their orbits are in those orbits because that's a trough in the energy pattern coming out of the sun. And so we all ride in that trough. But as that energy pattern changes, it can accelerate, it can decelerate, and then it buffets us. But normally we try to ride in that trough. That's why we have that orbit around the sun. But there's a constant wind coming from the sun.
Yeah.
But it's the changes that bother us. Am I over my time?
No, you're fine. I just wanted to let everybody know VE testing will be in about 5 minutes in the library.
All right. And yeah, we're just about done too. So, any other questions?
I was just going to say that probably in theme with your presentation, the Warrensburg booth has some NASA stickers there.
Had some what?
NASA stickers,
Oh, really?
anyone who was,
All right. And I was supposed to mention, I guess in the beginning, I didn't do it. but the club wanted me to make a disclaimer that these opinions, especially the global cooling part of it and going into a mini ice age, which I am firmly predicting that we're going into, that is not the opinion of several of our club members.
We're gonna hold you responsible. Hey, by the way,
collusion in this message.
Tabitha Stove is now KM6UCO as of June 20th.
All right.
Yeah, and it's
Well,
Tabitha
you got to
T.
understand, the man you're competing against was the guy who invented the internet.
Yeah.
It's Tamitha, TAMITHASKOV, so I,
Yeah.
in case you guys probably all know, but for those.
Actually,
of us-
I'm into amateur astronomy, and I don't even know her just till now.
Yeah,
But
it's
then
kind
again,
of-
I was just read books, so.
Yeah, I try to highlight her on the on our working page. You can find her on YouTube, and she's got
Solar
a
Wave, she's
real
going
big
to.
Twitter presence.
Yeah, I guess she's
Solar
from
wave?
Slavic, like a Slavic country.
Solar weather lady is what
She lives in Woodland Hills, California.
Thank you.
So anybody learn anything?
Yeah, that was awesome. Yeah,
Good.
that was great.
So yeah, I mean, when people talk to you about global warming, yeah, there's global warming. And yeah, we had little to do with it, just little to do with it. But global cooling is going to trump everything.
Well, I've had conversation with people, and I'm like going, so far you've got to think about the carbon, and it's not the carbon dioxide. I tell you what, it has been proven that during drought conditions, you want carbon dioxide in your atmosphere, because what happens is when plants need to take in carbon dioxide to breathe. But during drought conditions, when they have to open up their pores to breathe, they're letting out more water.
Yeah.
So they can keep
Nature's
those
trying
pores
to
smaller
equalize.
and still breathe. You
Yeah.
get greening conditions like that's happening in all parts of Africa that haven't happened in 100 years.
Let me explain something else that's happening. You're noticing a lot of volcanic and
Yes.
and
Yep.
earthquake activity.
Yeah.
Seems to correlate, doesn't it?
Yep.
It does.
Now, what's interesting is it does, like you were saying, the Earth tries to balance
Yeah.
itself out when there's,
Exactly.
it tries to fix itself.
Anybody studying thermodynamics? No engineers. Thermodynamics is equalization. It's trying to equalize. So when you turn off the spigot, you turn off all the energy coming at us from the sun, it's cooling down. It's definitely, the last 30 years, it's been cooling down. You know, we're in the maximum period, we've been heating up pretty bit, but it's cooling down. And the Earth sees that. And so all that energy that's been hitting us for the last several decades in this maximum period, it's stored up. It's stored up. It goes into the core. It goes into the volcano layer and all that stuff. It's there. The energy doesn't get destroyed. But now that we're cooling, the surface is cooling, the Earth is the same weight. I still have all this energy in here. So it's rising up. It's coming up to the surface. Nature is trying to balance. And so not only do we have the weather extremes where we've got the Earth trying to cool off in one spot, but we still got stored up energy here in the tropics or whatever, so it's getting wild, isn't it? Storms are getting more intense. And the ring of fire thing, the volcano activity, all that stuff, there's reasons this stuff is rising up. We are going into a very interesting time to be on this planet.
Yeah, they just closed Yellowstone.
Yeah,
like a
big
couple days
fissure,
ago. Yeah.
Yellowstone opening.
Well, there's no Yellowstone's a caldera. About
Yeah, caldera's
35,000
like-
years.
That's a super volcano. If it goes,
Yeah,
it's a life-ending event.
Wow.
yeah. Every about 4 or 5 states around there better just have a very heavy umbrella, and they're still even survive.
But, you know, so that all feeds into what we're seeing. The more volcanic activity because the Earth is trying to balance out. The crust is becoming cooler. All that energy is still stored up there. So then we get these volcanic eruptions. Look at Hawaii. And all the carbon dioxide coming out of that, all the ash. So the ash is in the atmosphere. Guess what? That's cooling us down some more.
Yep. Sure is.
According to Roy Spencer, who's a climatologist at NASA, water vapor is a much more potent greenhouse gas,
Yep. Yeah.
orders of magnitude.
Absolutely.
CO2, and even carbon monoxide, which is not, carbon monoxide is not good because that's your acid rain. That's what, you know, it goes up, gets into the atmosphere, gets into the clouds, and carbon monoxide, well, carbon monoxide is corrosive. It is a carcinogenic. And it starts raining. Next thing you know, people start getting cancer in their skin. Well, you just got rained on for the last 3 years with acid-producing chemicals.
It's all these extremes you're seeing out there, this weird weather pattern we're in right now, where it looks like it's springtime and in summer, with the storms we just had this last week. All this has reasons. And, you know, there's always science behind it somewhere. But thermodynamics really teaches us a lot about what's happening right now and why we're seeing extremes on one spot of the Earth and then it's super cool on the other side of the Earth. You look at the global average temperature and you can see that we are declining. We are going into this cooling period. And it's just going to get worse.
How much temperature change do you expect in the next, say, 50 years, average, down?
They say 1/10 of a degree in a year is extraordinary. So it's not going to be a lot, but then again, I mean, that experiment on 9/11 when all the planes went out of the atmosphere and we went up 3 degrees, we know it has a lot to do with particulates and everything else. So we really don't know. You know, we're in such an unknown. You know, we're just now starting to figure out weather patterns. You know, we got all these computer models now that they're getting pretty good at predicting weather. But this is throwing a loop in all of it because there's no other way to explain why California is experiencing extreme heat and setting records. Dallas is setting records, and we're cool. And the computer models show us that it is mixing from cooler areas, and that there are areas that are trapping heat, like the tropics, and cities, and things like that. So we're experiencing a balancing out period, and all this is mixing together, and we're seeing the violent extremes between all these. But you know, as we start cooling off and the volcanic activity continues, earthquakes continue, all this stuff, it's just going to build on it. And it just all adds together to building what we're predicting, this mini ice age.
It's all got something to do with something unless it's something else.
Man, that's true.
How things are more like they are now than they ever were before.
Yeah.
Well, you got to think about it also in the grand scheme of things. People think, well, we got all this technology, we got the turbo compression engine, we got carbon blast.